Good day, folks. Here's another question. It's an object that is pulled at an angle. It's a work energy and power, but it infuses or it requires the Newton's law background. A worker pulls a crate of mass of 30 kg from rest. Very important, from rest. That means the initial velocity is zero along the horizontal floor, applying a constant force of 50 newtons at an angle to the horizontal. So here's the crate. It's pulled from rest with this force at an angle of 30. The crate is 30 kg. And the displacement is what? Is 6 meters. So the crate is pulled to here, to this point. So there's a final velocity there. Right? And since it's pulled at an angle, there are components there. There will be an fx there and an fy there. It's very important. Now, question 5.1, it says draw a label free body diagram showing all the forces acting on the crate. Guys, grade 12 is very important. This year, when it comes to free body diagram, you do not show components. It has been changed since last year's examination, the November examination. So you don't draw the components, you just show the forces. So our free body diagram there, it's going to be the normal force, the gravitational force, and the force applied. The force applied and the frictional force. The frictional force, and we are told there the frictional force magnitude of 20x to the crate while it's moving. So we have a frictional force there. That's the free body diagram that you show. The components you do not show this year. It has been changed, guys. Now 5.2, it says give reason why each of the vertical forces acting in the crate do not do work. So do no work on the crate, guys, all the time. So the answer for that, the vertical forces, they do not do work because they act perpendicular, right? They act perpendicular. So one option there, you can say their work done, change in x, cos 90 is equal to 0. You will get the marks when you show that because they're doing no work there. So they act perpendicular. Or what you can say angle, this is an alternative, angle between the force and displacement. Displacement is what? Is 90 degrees. Yeah, and so forth. You can say the crate moves horizontally and the x, the force x, the crate moves horizontally and the crate moves vertically. So yeah, that's 5.3. That's what you can say there. 5.3, it says calculate the work, the net work done on the crate. It reaches point P, starting point O. So calculating the net work done there. So how are you going to calculate that? The net work done there, you say work net is equal to all the forces that are acting there, that are doing work. It's the work done by friction, work done by applied force, but the applied force x, the horizontal one. So those are the forces that are acting there. So the work done by frictional force is Fk, change in x, cos theta, plus the work done by Fx, you say Fx, which is Fx is F cos theta. This is Fx, and then change in x cos theta, right? And then we substitute. What is our friction there? We are told it's 20. From the statement, it's 20. And then our displacement is 6, right? It's 6. And then the friction x in the opposite direction. And then the force applied there, it's 50. 50 cos 30. 50 cos 30, right? And the displacement is what? 6. And then cos the fx, x in the same direction with the displacement is 0. but the frictional force acts in opposite direction. So that's why it's 180. So this is 0 degree. So when you punch that in the calculator, when you calculate that work net, it will give you 139.81 joules. Remember, the work net or the work done is in joules, right? So there are many ways to do that, guys. There are many ways to do that, but we're going to stick on that, right? So let's go to the next question. Use the work energy theorem to calculate. Okay, let me show you another way of doing that. Let's calculate the F net first. Forces that are acting there. So it's the force applied horizontally, and then it's the Fk, and then it's going to be F cos theta, and then the frictional force, since it's negative, it's going in the opposite direction, so it's going to be, okay, I'll just say negative Fk. Negative Fk, it's going to be 50 cos 30, and then the frictional force is 20. So when you punch that in the calculator, you get 23.30 newtons. That's the F net. After getting that F net, so I will calculate the net work done. The net, the work done by the F net, which is work net is equal to F net change in x cos theta. Since the answer here is positive, it simply means that the F net is going in that direction and the displacement is going in that direction. So the angle between them is 0. So the F net is 23.3. The displacement is 6 cos what? 0, as I've mentioned there. So 23.3 times 6 cos 0, it's going to be 139.81 joules. That was an alternative. There's another one, guys, but I'm not going to do that. Okay, 5.4, use the energy theorem to calculate the speed of the crate at an instant it reaches point B. So we wanted the speed as it reaches here, and we were told to use the work energy theorem. That's 5.4, right? So work energy theorem, it's work net equal to change in Ek. So now the forces that are acting there, it's still the work force by the frictional force, work done by frictional force plus the work done by Fx is equal to change in Ek, right? So in 5.4, so since there's no need for this, guys, there's no need for this, my bad, so you have to use the work net since we have calculated the F net. So there's no need to do that, you have done that already. So here okay, let's do this. So here you just say half mv v squared v initial square, and then here when we substitute, you substitute that work net, the net work done, and then the mass of that object. What was the mass of that? It's 30 kg, so it's 30 times the v final is the one that we want, the v initial, the initial velocity of that, it says it started from rest. So this is going to be 15vf squared only, and then you have 139.81 there. So you divide by 15, and then you put the square root, and then the final velocity, it has to be greater. So it's 3.05 meter per second, and that's the final velocity there. So guys, that's what we're going to use. That's what we're going to use there. So 5.5, it says the worker now applies a force of the same magnitude but smaller angle to the horizontal. on the crate, right? So the worker now applies the force with the same magnitude but smaller angle. So it's the same force, but the angle is there. So the angle is smaller. It's the same force, that is 50. So what is happening now? Now, what is the question there? So the angle has been decreased there. So what is the question? It says, how does the work done by the worker compare to the work done by worker in 5.3? Write down greater or smaller or equal to. So guys, what's going to happen when you decrease an angle there? When you decrease an angle there in 5.5, so okay, let's start by greater or smaller. So it's going to be greater, guys. The work net there, the work net is going to be greater. It's greater than. Why? So guys, when angle decreases, the fx increases. So if fx increases, the fnet increases. So if fnet increases, that means the work net also increases. So that's why it's greater than. All right. So that's the explanation there. So the horizontal component, which is the fx, it's going to be greater now, and the fnet will be greater. Or alternatively, you say as the angle, come on, as the angle decreases, cos theta increases. The cos theta increases, so therefore fx will increase if the cos theta increases, right?